this year we have several new team members. I will start off with mentioning team leads. First I'll represent me, Everett Allen. We also have Ruth as team lead. Under 3D design, we have Kayla Gardner and Son Richardson. Under the building team, we have Landon Knight and Dallas Abbott. Under electronics, we have Josh Song and me. Under programming, we have Landon Knight, Ruth Edwards, and Diego Dominguez. I'd also like to mention our advisors, Cindy Clements, Earl Nesbitt, Hayden, Karen, and Caleb. Thank you. Next slides. Our design goals for this year were to create a swarm of drones that will navigate the sand dunes and communicate dangers back to the Hive Tower, which is our central communication hub. All drones will be autonomous and able to navigate the sand dunes. Next slide. Design. Next slide.
This year's swarm concept has given our project a great deal of operational redundancy, meaning that we can run all of the courses even if several of our drones are incapacitated. This has the additional benefit of giving us the flexibility to run multiple courses while at the same time repairing and modifying other drones. All drones this year were designed to be functionally the same, which means that they share the same sensors and navigation communication. They have a radio that allows them to communicate with the Hive Tower, which was used during our team's mapping demonstration. Modularity was also a central component of this year's design. All components on the drones are attached to a modular mount, which is then secured to the drone bodies. This modular mount can be moved to any drone and is also easily replaceable and has the added benefit of being easily redesignable for any components that need attention. This came in handy when late in testing we discovered that the infrared sensors on the bottom of the drone were too far back to detect pits in time. We were easily able to move the IR sensors to the ping mounts on the front of the drone. Without this system, we would have had to have modified or redesigned all 5 drone bodies. Next slide, please. On this picture, we can see a variety of the components and mounts. Starting from the front, we have the 2 ping ultrasonic distance sensors, along with the IR sensors for pit detection. On top, we have the bump sensor, followed by the XP radio, the range ultrasonic sensors. On the sides, we have the wheels, which are attached to the motors and the motor mounts. Next slide, please. This year, we embraced an iterative design and building approach, which means that, as you can see, we have the drone body and the wheels. Starting with the drone bodies, we started with a foam core flat pack design with box joints. This was used as a design pathfinder to ensure that all internal components had adequate room to fit in properly. Next, we moved to an acrylic design of the same specifications, followed by a 3D printed and finally a 3D printed design with internal component mounts. Each design was built, tested, and improved for the next version. Moving on to the wheels, we started with 2 designs from the last year's robots, as well as 1 design for the year prior to that. We rescaled all of the wheels for the robots to be the adequate size for our drones and tested them. Upon testing, we decided that a modified version of the wave wheel seen in blue worked best for our drone this year. In general, each year the wheels are a modified version of previous year's wheels, which is just another example of how our team has implemented the iterative design process. Next slide.
Electronics. Next slide. This year, all 5 drones have their own custom central board design, whilst the towers have their own custom design, meaning we have 2 custom PCBs for this semester. Meanwhile, the drones themselves have a variety of modules and sensors that allow them to move, navigate, and map through different terrain. All of these sensors and components are then controlled by a 40-pin parallax parallax compeller chip. Seen on the right here is our electric block diagram for a single drone this semester. Next slide. The Hive Towers. The Hive Towers act as the central communication and mapping hub for the drones. As seen over here, the Hive Towers are static devices placed upon tripods. Then they are placed a set distance apart from each other in the formation of a triangle. We make a specific difference between a central tower and the two secondary towers, but there's no difference in their electronics, only in their programming. Next slide. The components. As already mentioned several times, there's a variety of components this semester, but a couple important ones to mention are the infrareds, the XBs, and the ultrasonic pings. The ultrasonic pings and the infrareds are what allow the drones to see walls and pits, whilst the XB allows them to communicate with each other via radio signals. Additionally, it's important to note that this semester we switched from our 0.3 amp per hour batteries to new 2.2 amp per hour batteries due to the large amount of components sucking up a lot of current. Additionally, our towers are far simpler than our drones, featuring only 3 parallax ultrasonic pings and XB, and then are powered via a 9-volt alkaline battery. Next slide. The power budget. A single drone this semester pulls in about 350 milliamps as long as it's not stalling. But if it is stalling, you, by average, pull in about another 200 amps. Next slide. I'll now pass it over to programming.
Next slide, please. So there are 2 main parts of programming for this project. First, we have navigation, which includes reading all sensors and avoiding obstacles. Second, which is mapping and communication, which includes syncing radios, communicating dangers, detecting distances, calculating coordinates, and creating a map. There's a total of 8 separate cores that are all running simultaneously within our program. Each core runs an essential part of our program. Next slide, please. The first part of programming is navigation. Navigation includes reading all sensors while looking out for obstacles. Once an obstacle is found, there's a specific action that our drone then executes for that obstacle. There's also a compass that tells the drone which way it should be heading. Next slide, please.
Our communication protocol seeks to synchronize all of our XB radios together. The first item in this protocol is that the main tower will send out an initialization signal as well as an ultrasonic pulse by which the drones can measure their distances. Then the second tower will send out its trigger and its ultrasonic pulse, followed by the third tower's signal and ultrasonic pulse. Then the main tower will request information from a drone. The drone will send back its status, which includes its distance from each of the 3 towers, as well as any obstacles it might have identified. This communication protocol actually works fairly seamlessly in that it keeps everything synchronized. If any of the drones, or if either of the 2 subordinate towers believe they have missed something in transmission based off of number of characters it received, whether that's too high or too low, or if something timed out and it believes it should have received something by now, then it will give up on that particular loop and cease receiving or transmitting. And it will wait for the next initialization signal from the main tower. Conversely, if the main tower believes it has missed anything in transmission, it will give up and go back to the beginning of the loop. Next slide, please. Our mapping scheme, while it changed many times over the course of this project, ended up with 3 towers. We have the first tower centered at the origin. Our second tower is at the top of the vertical axis, and our third tower is at the end of the horizontal axis as shown in this picture. Our drone will know the distances from each of the towers, and these distances between Tower 1 and Tower 3, as well as the distance between Tower 1 and Tower 2, are known to be about 4 meters. From here, we are able to use the formula for the area of a scalene triangle, and we divide it by the base, which gives us our altitudes of these 2 triangles, which are denoted by these dotted lines. These function as our x and y coordinates, which are then sent over to our mapping algorithm, which graphs our drone's position and any obstacles in real time. Next slide. will now discuss the outcomes of our project.
Next slide, please. So when we reached the Great Sand Dunes for our competition, we were able to complete 4 out of the 5 courses. Those courses being course 1, 2, 3, and 5. There were many difficulties we had to overcome once we reached the dunes, the main of which was when we were testing on our obstacle course, the sand was very hard and frozen. Once we reached the dunes, however, the sand was very dry and very loose. This caused our drone to move much slower than we thought it would, as well as have low clearance issues. There were also several pieces that needed to be replaced due to malfunctions, all of which were easily replaced because of our modular holding system. There was also a navigation adjustment that needed to be made so that our drone would head in the correct direction. Next slide, please. Course 5 proved to be one of our greatest challenges at the dunes. Course 5 featured a hill that had a steep incline that was difficult for our drones to overcome. It was partly due to the fact that our motors were not quite powerful enough and we had low clearance issues in our drones. To fix this, we took one of our drones, roly-poly, and begun to modify it. On your left, you can see roly-poly before the Great Sand Dunes, and on your right, you can see roly-poly after the sand dunes. First, we began by duct taping all the wheels so that sand would not get inside the wheels and weigh roly-poly down. We then flipped our motor mounts upside down to provide roly-poly with more clearance. This was easily done because of our very easily replaceable modular system for our motors. We then took the the bump sensor off the front of roly-poly so that it would not scrape across the sand in front of it. Once all this was done, we set roly-poly down and he was able to complete course 5. Next slide, please.
As we have well and thoroughly established, there was no shortage of difficulties over the course of this project. It is an engineering project after all. To take you to the highlights, our bump sensor was wired incorrectly, which resulted in the 5-volt regulator overheating, as well as the batteries draining extremely quickly. Also, the program would reset itself at seemingly random intervals due to this issue. Another issue we had in terms of general navigation, which was previously discussed, was that of pit detection. Finally, our mapping scheme was initially polar coordinates with one tower in which we were able to calculate the coordinates based off of a distance and an angle. However, in the final 2 weeks of testing, we realized that this was highly inaccurate and we had to make the last minute change to go back to 3 towers using Cartesian coordinates. Despite all of these shortcomings and failures, we cannot help but count all of our accomplishments this year as an overall success. Next slide, please.
We had several successes and achievements over the course of this project based on our initial design choices, including creating a modularized design that was able to navigate the sand dunes, along with creating our mapping and communication towers that were able to map and detect distances effectively. Next slide.
Budget. This semester, due to supply chain issues as well as the cost of our robots, we were forced to start cannibalizing and scrapping old drones from previous years, as well as completely emptying our stores of things like regulators, ultrasonic pings, and compasses. Still though, our budget for a single drone is about $600, with all 5 drones coming to about $3,000. Next slide.
Before we end this presentation, I would like to acknowledge a few of the people that helped us over the course of this project, including Space Grant, Advanced Circuits, Andy, our Parallax representative, and all our wonderful advisors. Thank you. Next slide. Thank you all for coming to